In this video, we're going to look at describing the location of the electrons in an atom. And to do that, I'm hoping some of this is familiar to you. We're going to get into quantum numbers and this quantum mechanical model of the atom, which is basically saying that, we don't believe that electrons just fly around in these Bohr orbits, which is kind of the typical freshman model of the atom, where we've got these rings around the nucleus and the electrons fly around in a circle. If that were the case, atoms would be two-dimensional and matter would be flat, which we know is not the case. So instead, we're going to put electrons in these three-dimensional regions around the nucleus. We're calling them orbitals. Hopefully that's a term that you've used in the past. An orbital is just this three-dimensional region around the nucleus where we have a good chance of finding an electron. There's a high probability of finding an electron. This is about the best we can do, is to say there's a good chance that I will find an electron in this region around the nucleus. Is it close to the nucleus? Is it far from the nucleus? But within this three-dimensional orbital, we'll never know the exact location of an electron. They're moving. They're constantly moving. So we call this the Heisenberg uncertainty principle, which basically states just that. We'll always be a little bit uncertain as to the exact location of the electrons because they're constantly moving. But using what we call quantum numbers, it's about the best we can do in trying to locate the electrons. Think of quantum numbers as kind of like an address where, you could give me your home address and that'd be kind of creepy. I wouldn't come and find you or anything. But that address would give me a high probability of finding you. Maybe after school's out or something like that. Within your house, I don't know exactly where you are. You could be upstairs, downstairs. You could be in the basement. You could be anywhere. You're constantly moving in that house. But by having that address, I would have a good chance of finding you. That's kind of how I think of these quantum numbers. And again, I'm hoping that this is something that you've seen in the past. The first quantum number is called the principal quantum number. It's described by the symbol n. It'll be a whole number integer. We can be more specific here, from 1 up to 7, with the elements that we are confident in at this point in time. We know of about 7 energy levels. Someday that will change. I'm confident that will change. But for now, we're going to say the energy levels are 1 through 7. And when we say that, there's an electron in the first energy level or the second energy level, we're describing a few things. We're listing the size and the energy level of the orbital. If I'm in energy level 1, well, that electron is relatively close to the nucleus. And we know if it's close to the nucleus, it's relatively stable. There's a good attraction between the nucleus and the electrons. That electron's not doing anything too crazy, hanging out in his little orbital close to the nucleus. As n increases, the electrons are found further from the nucleus. So as I go to the second energy level or the third energy level, I'm describing the distance from the nucleus where I'll find that electron, which is something I kind of like to add in here. The size of the energy level and the amount of energy, and also let's add the distance from the nucleus. So obviously as I go to energy level 3, 4, 5, 6, 7, those electrons are further and further from the nucleus. Now a couple things happen here. Obviously the orbital is larger. The electrons tend to spend more time further from the nucleus. Look at these last two. The orbital is at a higher energy level as n increases. The electrons are not as tightly bound to the nucleus, which we'll talk about a little more when we get into some periodic trends. These last two can create an unstable situation. So as the electrons are further and further from the nucleus, they're at a higher energy level. Higher energy is not stable. And they're also not as tightly bound to the nucleus. Opposite charges attract, but if you got these electrons that are really far from the positive nucleus, that attraction weakens. That leads to electrons that are vulnerable, electrons that may be removed from the atom at some point in time. So this n, the principal quantum number, is super easy. Just describes the energy level, the distance from the nucleus. Second quantum number, now don't freak out here, it's called the angular momentum quantum number, which is symbolized L. I don't know who picked L. It doesn't seem logical, but it's an L. Now the nice thing is you don't have to worry about that. You're not going to have to know it's the angular momentum quantum number. We just need to know that the second quantum number describes the path that this electron typically travels around the nucleus. Or in other words, like the shape of the orbital. So you may remember that there are different shapes of orbitals. That by studying data on moving electrons, we find that they tend to move around in these different spaces around the nucleus, and that creates different shapes, regions where there's a high probability of finding an electron. So I'm hoping that you remember the s orbital. S orbitals are sphere-shaped. Oh yeah, that makes sense. And again, now as we start putting these quantum numbers together, we can have the 1s orbital, the 2s, the 3s orbital. The first quantum number tells me the distance from the nucleus, and the second quantum number tells me the shape of the orbital. So if I have 3s, that tells me that this is an electron in the third energy level, so it's relatively far from the nucleus, and it's an electron that's moving in a sphere-shaped region around the nucleus. And again, I'm picturing this as a three-dimensional region around the nucleus. So another thing that I like to make note of here is that, as that first quantum number increases, that principal quantum number, the orbitals get larger, which basically just means that the electrons, again, tend to spend more time further from the nucleus. But if I have s orbitals, the electrons are all kind of traveling in this same sphere-shaped region. Now they also add here that there's 1 in every energy level. There's a 1s, 2s, 3s, 7s. And there are also something called nodes, which are areas where there's a lower chance of finding electrons. We'll kind of mention nodes in a little bit. The second shape of orbitals that we should mention is the p orbital, and I'm hoping that these are relatively familiar to you as well. P orbitals kind of have this, they call it the dumbbell shape, where it's like two lobes, and in the center you'd have the nucleus, so we kind of call that a node again, an area where there's not a high chance of finding electrons, like right smack around the nucleus. They're in these two lobed regions around the nucleus. And again, as that first quantum number increases, the size of the orbital increases. But we should note here with these p orbitals, they're a little bit higher in energy than s orbitals. They're also larger than s orbitals. So you won't find these p orbitals in the first energy level. So it says every energy level beyond the first. So there is no such thing as 1p, which is something that they may try to trick you on. They might say, like, how many electrons can have the quantum numbers 1p? And we would say 0. There is no such thing as 1p electrons. They don't start until the second energy level. So here they have these examples listed, and they've got 2p. Now, if I had a 3p, let's see if we can scoot this in. Let's say it was a 3p orbital. It would look real similar. It would just be larger. Same shape, just a larger region around the nucleus where I may find electrons. So all the way up to like a 7p with same shape, this kind of two-lobed, dumbbell-shaped orbital. It would just be giant in orbital terms. So again, these aren't found in the first energy level, not till the second. They're too big, they have too much energy. There's 3 of them in every energy level, second and beyond. And again, they're all the same shape. They just lie on a little different axes in space, which we'll mention in a minute. So they've kind of got this listed as 2px. So this guy's on the x-axis, 2py on the y-axis, and 2pz going up and down on the z-axis. Exactly the same shape, same energy. They're just lying in a little bit different orientation in space. Now, every orbital, whether it's an s orbital, a p orbital, or whatever kind of orbital, can hold a maximum of 2 electrons. So all of these orbitals can take 2 electrons. Now, we don't know exactly where those electrons will be found at any given point in time. There could be 1, 2. Maybe they're both in the same lobe. There's 2 electrons. Maybe one's kind of over here and one's down there. I don't know. Every orbital has a maximum of 2 electrons. Even s orbitals can hold maximum of 2. So if all the p orbitals were filled, we could hold up to 6 electrons. Maximum amount of electrons you could find in all the p orbitals together would be 6. So one thing they might do now is say like, okay, there's no such thing as 1p electrons. What about 4p? They might say, how many total electrons could fill the 4p electrons? And so I say, okay, 4th energy level, can I have p orbitals? Absolutely. 4p could hold a maximum of 6 electrons. Every energy level beyond the 1st can hold a maximum of 6p electrons. You may have mentioned the d orbitals in first year chem. The d orbitals are real high energy. They're kind of these unstable electrons. This is the transition metal group. Here's that transition metal region in the middle of the periodic table. That's the D block of the periodic table. These things are a little crazy. They've got 4 lobes separated by a node again, which is the area where you'd find the nucleus. They also increase in size and energy as n increases, which just means that if I have 3d orbitals versus 5d orbitals, the d orbitals in the 5th energy level will just be bigger. They'll have more energy and they'll be larger in size. The electrons are further from the nucleus, but they'll have the same general shape. Since these things are pretty high energy orbitals, you will not find these guys till the 3rd energy level. 3rd energy level and beyond. So again, they could try to trick you and say, how many electrons will have the quantum numbers 1d? And we would say, none. There is no such thing. How about 2d? Trick question. You will not have d orbitals in the 2nd energy level. You won't find the d's until the 3rd energy level and beyond. There are 5 d orbitals in every energy level, 3rd and beyond. They can each hold 2 electrons for a maximum of 10. And so again, they all have, well, for the most part, the same general shape. Just this guy on the end. Sometimes this one's called the donut orbital, where 2 of the lobes kind of join in a ring around the center. But they're all equal energy. Even the donut orbital carries the same amount of energy as the rest of them. Most of them have these 4 lobes. They're high energy orbitals, not found till the 3rd energy level. They're just lying on a different plane in space. And so again, there could be 2 electrons maximum. We don't know exactly where. They could be kitty corner. They could be side to side. I don't know. They could be in there. They could be opposites. There could be one in the donut, one up on top. I don't know. But I know that they could hold a maximum of 2 electrons each for a total of 10. The last shape of orbital that you may not have mentioned too much about in first year chem are the f orbitals. These things are crazy. For the most part, they've got 8 lobes separated by a node in the center. Although, again, there are a couple kind of goofballs that have these little donuts around them. These aren't found until the 4th energy level. They are too large, and they're too high in energy for the 1st, 2nd, or 3rd energy level. You won't find these till the 4th. And again, they get bigger as n increases. So a 4f orbital would be smaller than a 5f orbital. Same general shape, just on average, a 5f orbital would have electrons that are higher in energy and further from the nucleus. There are 7 of them. Here they are. They're nuts, which means they can hold a total of 14 electrons. Each orbital can hold 2 maximum. I've got 7 f orbitals for a total of 14 electrons. Okay, so that was the second quantum number. It's actually a letter. S, P, D, or F, which describes the shape of the orbital. The last 2 quantum numbers, one of them is called the magnetic quantum number, symbolized M sub L. You don't need to know that. We just have to know in general, what is the third quantum number describing? The third quantum number is the orientation, or like the axis in space. This third quantum number will identify one particular orbital when more than one exists. The most common example is with like the p orbitals. There's a p orbital on the x-axis, the y-axis, and the z. So that little x, y, z, that's the third quantum number. So somebody could say, how many electrons could have the quantum numbers 3p? And if all I saw was 3p, I would say, well, that could be up to 6 electrons. But by putting the next quantum number in, how about 3px? Oh, well, now that's singling out one particular orbital. There are 3 to choose from. In the third energy level, there would be a p orbital on the x-axis, y-axis, and z-axis. This is specifically pinpointing the p orbital on the x-axis, which narrows it down to 2 electrons. It narrows it down to like roommates. These 2 electrons are sharing an orbital together. How cute. Now when you get to like the d orbitals, you'll see kind of like 2 little symbols. Like this could be the d on the xz axis. And again, that's just trying to describe the plane. But that xyz stuff, that's there to narrow it down to one specific d orbital when more than one exists. You don't have to memorize the different axes and all that good stuff. We just have to know in general that if I saw something like 3d, that could be one of any 10 electrons. If I saw 3dxz, that's one of the particular orbitals. That could be 2 electrons. One orbital, d orbital, in the third energy level, it could hold a maximum of 2. The last quantum number is the spin. And again, you don't have to worry about the m sub s and anything like that. We just have to know what this means. At the end of a set of quantum numbers, you're going to see this plus or minus 1/2. When you have 2 electrons sharing an orbital together, and they're constantly moving, they create a magnetic charge. This magnetic charge causes the electrons to spin, And if there's two electrons in an orbital together, they'll always spin in opposite directions. So now this plus or minus 1/2 is kind of arbitrary. We would say one of the two electrons has a positive or forward spin. One of the two electrons has a negative or reverse spin. Totally arbitrary, which is plus 1/2 or minus 1/2. We just have to know that they're spinning opposites. So now what I could do is string these all together, and this is the best I can do. If I wanted to locate one stinking electron, I could say, this is an electron in the third energy level. It's in a p-shaped orbital. Oh, it's one of 6. It's a p orbital on the x-axis. I've narrowed it down to 2. The last quantum number would either be plus or minus 1/2. That's the best I can do. That narrows it down to 1 electron. Now the tricky part is that that 1 electron is constantly moving. This is the best I can do. And we can do the same thing with the D's. We could have the 3dxz minus 1/2. That brings me to 1 electron. Best I can do. So again, it's kind of like an address. Now finally, we should mention something called the Pauli exclusion principle, which basically states that in an atom, no two electrons could ever have the same set of 4 quantum numbers. We could have electrons that have 3 electrons, 3 quantum numbers the same. We could have somebody that looks like 3px minus 1/2. These guys are roommates or orbital mates. I had friends that were twins. They called each other womb mates. Get it? Womb mates. Now this makes sense. It's kind of like no two houses or buildings would ever have the same address. That'd be ridiculous. You'd have mail coming to different spots. It's kind of the same thing with electrons. No two electrons will have all 4 quantum numbers the same. They could have the first 3, and then we're talking roommates. But they would always spin opposite. So I'm hoping now that if we narrow this down to these quantum numbers, we've got the energy level, the shape of the orbital, the axes of the orbital, and then finally the spin, that this may be something that's familiar to you. I'm hoping that you've looked at this in the past, and this was a good refresher on locating electrons using quantum numbers.